James Webb just returned data that rewrites the entire story of 3I Atlas, and none of it matches the behavior of a natural comet. Its trajectory is no longer a simple flyby. The new readings point toward a direct intersection with Mars. At the same time, Atlas is emitting rhythmic bursts of energy and signatures of engineered material, raising questions about whether this object is moving under its own control. And as these signals intensify, Mars itself appears to be responding with seismic activity and unexplained radio patterns, a combination no one expected to see. In this episode, we're breaking down what Webb actually detected, why the trajectory matters, and what a collision scenario could mean for the red planet. If clear, curiosity-driven analysis is your thing, consider liking and subscribing. Let's begin. The first confirmed sighting of the object, known as 3I Atlas, came on the first day of July, and the early data suggested something familiar: an interstellar traveler crossing the outer regions of the solar system. At that stage, it appeared no different from the few interstellar bodies previously observed. It showed a bright coma, a fast streak of motion, and a velocity that stood out immediately. Instruments measured the object moving at nearly 87 kilometers per second relative to the Sun, which reads as 87,000 meters each second. At that pace, it could move from the distance of Earth to the distance of the Moon in less than 80 minutes. This alone placed it in a rare category. But speed was not what caught the attention of researchers. As additional observations came in, the behavior of the object began to diverge from what is normally expected from natural bodies. Most comets entering the inner solar system lose speed as their paths respond to the Sun's gravity. Many break apart or release dust in wide arcs because of heating. Others settle into more stable motion as their materials begin to evaporate in predictable patterns. 3I Atlas did not follow these familiar paths. Instead, it began showing a steady increase in velocity. The increase was small at first, but the rate held firm over multiple days of measurement, which made it difficult to explain through natural outgassing alone. At the same time, changes in its trajectory became visible. The curve of its orbital path grew tighter, as though a sequence of small adjustments was taking place. These adjustments were tracked across independent observatories and matched closely, which ruled out random fluctuations or amateur error. The bright haze around the object, known as the coma, also shifted in a way that surprised observers. Comas usually change with temperature and distance from the Sun, but they rarely double in brightness in such a short period, unless the comet is breaking apart or undergoing a major burst of activity. For 3I Atlas, the brightness increased over several weeks without signs of fragmentation. Spectral readings added more questions. Ultraviolet light spiked far above what models predicted for an object of its size and composition. Carbon dioxide was released at a rate beyond known examples of natural sublimation, the simple warming and vaporizing of frozen materials. These signals pointed to a process more structured than chaotic jets caused by sunlight. They suggested repeatable activity instead of sudden bursts. Then came the results from the deep field sensors aboard the James Webb Space Telescope. These sensors are built to detect faint changes in light intensity and can reveal subtle rhythms that normal instruments overlook. When the data were reviewed, researchers noted pulses coming from the tail of the object. Comet tails often show irregular jets as sunlight heats pockets of ice, but the signals here were consistent. The pauses between each pulse measured exactly 17 minutes. This regular spacing made the pattern more like timed thrusts than natural jets. It implied that the outgassing was not only strong enough to alter motion, but also arranged in a controlled sequence. Similar timing was later confirmed by the Gemini South Observatory and by analysts at the Jet Propulsion Laboratory. The matching pattern across these independent facilities removed doubt that this was a measurement error. As this information accumulated, new orbital projections were run. With each update, a clearer picture emerged. What first appeared to be a distant pass turned into a near approach to Mars, with a calculated minimum distance of roughly 1.95 million kilometers. That distance might sound large by human standards, but in planetary dynamics, it is narrow enough to raise immediate concern. More complex simulations showed that even a small increase in velocity around 10 kilometers per second, which is 10,000 meters each second, would shift the object's path into a direct intersection with the planet. The key detail was that the energy needed to cause this shift was much smaller than the energy already detected in the observed gas pulses. This meant the object was close to a threshold where even one more controlled outburst could place Mars directly in its path. Scientists studying these changes noted another detail that deepened the concern. The direction of each thrust aligned neatly with the planet's orbital plane, instead of being scattered randomly. Natural comets do not fine-tune their outgassing to align with the orbit of a target. Their jets point wherever internal ice pockets happen to warm, but the movement of 3I Atlas looked selective. The more it adjusted, the more its course fit the exact geometry needed to approach Mars with precision. The projected period between the 19th and the 30th of September became a window researchers monitored closely, because a single large outburst within that span could alter the trajectory enough to result in impact. The pattern seemed intentional rather than incidental, and more scientists began to acknowledge that the object no longer fit the profile of a drifting fragment of ice and rock. Attention increased further when Avi Loeb, a well-known astrophysicist from Harvard University, released an analysis with his team. Loeb is recognized for proposing testable explanations for unusual astronomical events and for his work studying objects entering the solar system from interstellar space. His paper suggested that 3I Atlas might not be a natural body at all. According to his group, the combined data pointed toward the possibility of an engineered object. The hypothesis was bold, but it did not contradict any measurements gathered so far. Loeb noted that the rhythm of the thrusts, the extreme speed, and the precise alignment with Mars's orbital plane all matched behavior that natural comets do not exhibit. More information came from radar studies. The Mars Reconnaissance Orbiter, which carries instruments capable of sending radar waves across large distances, aimed its sensors toward the object. Ground-based radar systems, including the Goldstone antennas, did the same. Radar reflections from normal comets tend to produce soft signatures because comets are made of dust, water, ice, and porous rock. These materials scatter radar weakly, but the signals bouncing back from 3I Atlas appeared dense and sharp, more like echoes from compact metallic surfaces. Teams reviewing the data described the results as unlike any previous cometary radar profile. Internal sources familiar with the analysis said the reflections lacked the diffuse qualities expected from natural icy bodies. A different type of observation came from high-exposure images taken by experienced amateur astronomers. They captured narrow green streaks extending from the object. These looked like thin, concentrated streams pointing toward Mars. The brightness of the streams pulsed in a rhythm that matched the 17-minute emission cycle identified earlier. Because these images were long-exposure frames, they recorded changes in light over time and revealed structure that quick snapshots could not. When combined with the spectral and radar data, the picture grew more consistent. The object was operating in a pattern that did not match conventional comet behavior. Loeb's team considered the possibility that 3I Atlas could be carrying something to Mars. The nature of that payload was not specified because no direct evidence exists for its composition or purpose. They simply examined what the observed behavior allowed and concluded that the approach resembled deliberate targeting rather than a random crossing. Mars has an atmosphere far thinner than Earth's and a surface known to hold complex minerals and traces of ancient water. If an object were guiding itself toward a planet in the inner solar system, Mars might represent a strategic destination. Whether the intention was to crash, deliver material, or deploy some unknown mechanism could not be determined from current measurements. For now, researchers continue to track the changes in the object's motion and energy output. The consistency of the thrust pattern, the unusual radar echoes, and the refined trajectory all suggest a level of control that natural processes struggle to explain. With each update, the path grows more defined, and the uncertainty surrounding the object narrows. Scientists studying the data emphasize that every known natural model fails to account for the combination of features observed so far. 3I Atlas behaves as though it is adjusting its own motion with purpose. Mars stands directly along that line, and the next series of measurements will determine how close the object intends to come. When researchers modeled the possible outcomes of a direct collision between 3I Atlas and Mars, they began with simple numbers and converted them into forms that could be understood in physical terms. The object's estimated mass was around 10 billion tons, which means 10 billion metric units of 1,000 kilograms each, moving at a relative speed of 57 kilometers per second, or 57,000 meters each second. The kinetic energy of impact would rise to a level that is difficult to describe in everyday experience. Calculations placed the total release above 2 million megatons of energy. 1 megaton is equal to 1 million tons of TNT. 2 million megatons means energy thousands of times greater than the most powerful nuclear device ever tested on Earth. With values on this scale, the question became not whether Mars would be damaged, but how much of its surface and near-space environment would be altered in a single moment. Models built from past crater studies suggest that the point of impact would excavate a basin roughly 60 kilometers across and about 5 kilometers deep. The shock wave would push material outward at extreme speed, sending debris high above the Martian sky. Some of that ejector would settle back onto the surface. Some would remain in orbit temporarily. Some might be launched into solar orbit and continue drifting through space. A small fraction could, over long time spans, cross paths with Earth. This scenario is not speculation. It is a recognized possibility whenever a major planetary impact occurs. But while the physical consequences are serious, the long-term scientific consequences would be even more disruptive. Mars holds decades of data collected by multiple nations. It hosts orbiters that have tracked atmospheric change through full Martian seasons. Rovers have sampled minerals that record the planet's past climate and water cycles. Instruments have measured radiation levels, dust storms, patterns in surface chemistry, and potential biosignatures in soil. An impact of the magnitude projected for 3I Atlas would erase many of these assets instantly. It would bury or vaporize machines that took years to reach the planet. It would interrupt climate records and end experiments designed to detect signs of biological activity. Communication systems linked to Earth would be lost or damaged, which means information needed for recovery would disappear at the very moment it was most required. These concerns reached agencies across the world: the European Space Agency, Roscosmos, the China National Space Administration, and the Japan Aerospace Exploration Agency opened planetary defense discussions. These were not conversations about preparing for an alien fleet or a science fiction scenario. They were ordinary reaction meetings held because one object was demonstrating behavior just organized enough to raise questions about intent. The more closely its movement was studied, the harder it became to treat it as a standard comet. Mars itself carries its own scientific value beyond hardware. For years, evidence has suggested that the planet may have once supported liquid water on its surface. Recent studies have pointed to features beneath layers of frozen ground that could hold subsurface lakes or pockets of briny water. Some researchers believe that dormant microbes might exist in these deeper layers, protected from harsh radiation by the crust above them. If a massive impact cracked open those layers, the event could expose materials never touched by human instruments. It could also disturb ancient environments in unpredictable ways. If the incoming object carried organic molecules, unusual chemicals, or engineered compounds, those materials could interact with Martian environments in ways that Earth-based models cannot forecast. The collision would create temperatures high enough to melt rock, vaporize surface material, and generate long channels of heated ejecta. These extremes could open pathways to the deeper crust. The combination of deep Martian materials and any compounds released by the object could create new chemical conditions not seen before. Some biologists refer to this as a reverse form of panspermia. Instead of life spreading from Mars outward, new biological or pre-biological materials could be introduced into Mars. This idea raised questions about intention. If the object was not natural, and if its behavior suggested controlled motion, then its arrival near Mars could represent a delivery rather than a crash. The possibility could not be proven, but the data did not rule it out. As the object approached its closest projected distance to the planet, the James Webb Space Telescope was used to collect one final deep scan. Webb's instruments, including the near-infrared spectrograph and the mid-infrared instrument, detect faint molecular structures by measuring light at precise wavelengths. They can report the presence of specific gases, isotopes, and complex compounds in objects passing through the solar system. The results of this scan were held internally for 48 hours before a partial summary was released. Within that window, information leaked from individuals familiar with the raw data. Those leaks described traces of synthetic polymers within the object's emissions. Synthetic polymers are long chains of molecules created through manufacturing processes. They resemble plastics made on Earth and do not form naturally in deep space. Mixed with these polymers were patterns consistent with carbon nanotubes, which are engineered structures built from carbon atoms arranged in a cylindrical pattern. These materials require controlled conditions to form. They cannot be produced by simple heating of ice or dust in space. The spectrographs also identified isotopic ratios that did not match those found in known solar system objects. Isotopes are versions of elements with different numbers of neutrons. Natural bodies formed in the same region often share similar isotopic fingerprints. 3I Atlas, however, showed unusual ratios in both carbon and hydrogen. These anomalies suggested that the object either originated in an environment with different formation rules or was assembled through processes that do not occur naturally. In either case, the results supported the growing suspicion that the object contained engineered components. Webb's unfiltered data was then shared through private channels with major space agencies. Task forces were formed to evaluate the implications. Officials involved understood that there was no practical method to deflect an object moving at such high speed. The purpose of the meetings was analysis, not intervention. Even so, the tone of communication shifted. Public updates slowed. Several routine Mars telemetry feeds began showing gaps. Signals from missions like Perseverance and Tianwen-1 appeared incomplete or delayed. Questions asked during scheduled briefings were redirected. The pattern resembled a coordinated reduction in information, which often occurs when agencies enter a protection mode to avoid misinterpretation or public concern. The most significant change came from a leaked message labeled as a classified transmission. In that message was a short phrase, "Impact Protocol initiated." The wording was clear, but the meaning was not. Standard mission protocols include guidelines for power management, communication control, and safe mode operations. None of them involve dealing with an interstellar object on a possible collision path with a planet. People familiar with agency procedures speculated that the phrase described a coordinated response rather than an attempt at deflection. Some believed the signals sent to Mars-based equipment were intended to prepare instruments for impact. Others wondered if the transmissions were directed not at the machines, but at the approaching object itself. If 3I Atlas operated with any form of automated sensing, it might be capable of detecting electromagnetic patterns from orbiters, landers, and stations. When Earth-based systems transmitted new signals or increased broadcast strength, those changes might act as stimuli. To a natural object, such signals would be meaningless. To a guided or semi-autonomous system, they might represent a sign of awareness. This possibility raised concerns that activating certain systems might reveal to the object that its behavior was being closely monitored. If the object contained intentional programming or reactive behavior, these signals could influence its next steps. Whether this mattered or not could not be known, but the risk could not be ignored. During this period, a group at the Search for Extraterrestrial Intelligence Institute examined the available trajectory and timing data from the object. Their focus was not on sending messages, but on studying structure within the numerical relationships. They converted values such as velocity, time of closest approach, distance vectors, and gravitational parameters into binary form. This is a straightforward process. numbers are translated into sequences of 0 and 1. They then applied compression methods, commonly used in deep space communication, to see if any regular patterns emerged. The output was not random. Instead, it showed repetition within specific sections. The repeated segments matched intervals that corresponded to atomic numbers 6, 8, 14, and 26. These represent carbon, oxygen, silicon, and iron. In chemistry, these are fundamental building blocks. Carbon forms the basis of organic molecules. Oxygen is vital for many chemical reactions. Silicon appears in many structural and electronic materials. Iron forms the cores of planets and is central to many engineered alloys. Seeing these numbers appear in structured intervals suggested that the data reflected more than orbital mechanics. It pointed to a pattern built around elements essential to both living systems and mechanical systems, a combination that raised questions no one yet knew how to answer. The structured intervals identified in the earlier analysis were only one part of the pattern. When scientists examined the gaps between those values, they found something even more deliberate. The spacing included sequences of prime numbers, which are numbers divisible only by 1 and themselves. Prime numbers are often used in mathematics and coded communication because they are simple to verify and difficult to mistake for random noise. Their presence alongside atomic numbers suggested that the pattern inside the trajectory might not be accidental. Some researchers noted that the arrangement resembled the spacing used in recursive messaging systems, where a signal repeats in nested layers to preserve meaning even if part of it becomes distorted. This observation led to a new interpretation. The motion of the object itself could be carrying information. If this was correct, the flight path of 3I Atlas might represent a type of communication. Instead of broadcasting radio waves or light pulses, the message could be conveyed through behavior, timing, and position. A system observing its path would recognize patterns based on mathematical relationships rather than spoken language or symbols. This idea meant that the approach toward Mars was not only a trajectory to be measured, but also part of a larger sequence. The potential impact window could represent a type of binary outcome. A strike would convey one meaning, while a near miss would convey another. In this model, the answer existed within the motion itself. Observers were not simply watching a comet pass through the solar system, they might be observing a structured event. As simulation models refined the path, another detail emerged. The updated descent vector passed directly over a region on Mars known as Elysium Planitia. This area is considered geologically young because some of its features appear to have formed more recently than many other regions. Satellite images collected over years showed unusual formations there. These included ridges, arranged in nearly perfect circles, patterns resembling slow rotational flows, and structures whose spacing suggested mathematical consistency. Some of these features were described in terms of ratios similar to those seen in nature, but the overall arrangement stood out because of its symmetry. These patterns had been noted before, but they did not fit neatly into explanations involving volcanic activity or erosion. Near the center of this region lay a circular basin less than 3.5 kilometers wide. It did not match typical crater shapes, and it lacked debris patterns common to impacts. It also showed no signs of volcanic deposits. At its center was a material composed of crystalline silicates. Silicates are minerals made of silicon and oxygen, and they are common in many types of rock. What made this deposit unusual were its reflective properties. When exposed to sunlight, it produced brief, regular pulses of infrared light. These pulses were short and evenly spaced, a fact that researchers had often set aside because there was no clear mechanism to explain them. With the new trajectory, scientists reconsidered whether this basin was simply a geological feature or whether it had been shaped by forces not yet understood. As the James Webb Space Telescope regained a stable tracking angle on 3I Atlas, a different anomaly appeared. Instruments detected a second dark region trailing behind the main object. It was not physically attached. It maintained a distance of about 0.07 astronomical units, which is several million kilometers. This secondary region showed no signs of reflected light and no thermal signal. Radar scans failed to register any solid mass. Infrared detection found no warmth, even from scattered sunlight. Yet photometric measurements revealed a consistent drop in light when the region passed in front of background stars. The dark zone behaved like a moving shadow with clear boundaries. What made it more unusual was the precision with which it followed the main object. It did not drift. It did not show variation when the object accelerated or changed direction. When the data were plotted onto polar coordinates, the relative position of the shadow formed a stable orbital trace. This suggested that the dark region was bound to the object through a mechanism not influenced by normal gravitational behavior. It moved in synchrony, as though connected by a rule rather than by physical tethering. Scientists debated whether it might be a cloud of particles, a field effect, or a second object whose properties prevented detection by traditional instruments. Speculation widened. Some argued that it could be an artificial device maintaining a constant position to monitor or stabilize the main object. Others proposed that it might be a form of low reflective matter interacting with light differently from known substances. Another suggestion was that it might represent a memory field, a type of residual trace following the main structure. Without physical data, none of these interpretations could be confirmed. What researchers did agree on was that this second region behaved too precisely to be discounted as debris. As timelines approached the projected closest encounter with Mars, scientists reviewed the entire trajectory of 3I Atlas from its first detection. They examined the times at which it reached perihelion, passed Earth's orbital distance, and approached Mars's orbital plane. When those dates were compared with the positions of the inner planets, a pattern became visible. Each key moment occurred near astronomical resonance points positions, where orbital cycles align in simple ratios. Resonance is a principle found throughout planetary motion. When orbits match in certain ways, gravitational influences reinforce one another. Many natural systems show resonance, but the specific sequence here aligned with dates that have been noted across various historical records. These dates, September 23rd, October 5th, and November 11th, corresponded not only to equinoxes and predictable transitions, but also to alignment cycles repeating roughly every 54 years. Researchers pointed out that the last time the three inner planets occupied similar positions during the passage of a large object was during the Tunguska event in 1908, when a massive airburst occurred over Siberia. That event flattened large areas of forest and released energy comparable to tens of megatons. The similarity in orbital timing raised questions. An interstellar object arriving on such dates by chance remained possible, but the sequence of alignments reduced the probability significantly. As a result, some asked whether the timing was controlled. In academic discussions, the idea that an object might follow a schedule or respond to gravitational cycles is rare. Most comets follow paths shaped by formation and perturbation, but if 3I Atlas was adjusting its own motion, then it could be matching resonance points intentionally. This would give its trajectory a form of internal timing, similar to following a clock based on orbital positions rather than mechanical gears. This interpretation remained hypothetical, yet the repeating pattern encouraged further study. Researchers stressed that a pattern in astronomy does not automatically imply agency, but consistent timing often indicates a structured cause. Another development came from a team at Princeton University who study the relationship between neural patterns and external stimuli. Their work focuses on synchronization of brainwave activity. When volunteers were exposed to frequencies matching the 17-minute intervals detected in the object's gas emissions, their neural rhythms adjusted. This type of synchronization, known as entrainment, occurs when the brain aligns its electrical oscillations with an external pattern. What surprised the team was that individuals in separate rooms, unaware of one another and without direct communication, showed aligned patterns when the same frequency was applied. This response is not unknown in studies of coordinated auditory stimuli, but seeing it triggered by a modeled light curve from a distant object raised questions. The researchers did not claim that the object was influencing thoughts. They only noted that the rhythm it produced fell within ranges that human neural systems could respond to. This led some to consider whether the object's signal could have cognitive components in addition to mechanical ones. The idea was not accepted by all, and many pointed out that entrainment does not imply communication. Still, the coincidence of a naturally measurable frequency and the brain's ability to synchronize to it made the topic a subject of careful examination. As concerns grew, a separate group of archaeoastronomers began comparing the object's path with records from ancient cultures. Archaeoastronomy studies how early civilizations tracked the sky and interpreted celestial events. Scholars examined Babylonian clay tablets, Mayan codices, and Tibetan cosmology scrolls. These documents often recorded positions of comets, eclipses, and planetary alignments. When these records were compared with the modern projected path, the researchers noticed a recurring motif. It depicted a long, curved track across the sky that approached the region associated with Mars. Some cultures described a pattern called the flame serpent, which represented a moving celestial line that changed direction near the sun and approached the red planet. Carvings found in rock and illustrations on ancient textiles showed similar shapes. While these images are open to interpretation, the curve they depicted resembled the general motion of a long-period object bending around the sundial. The details varied, but the repeated association with Mars caught attention. Among these records, one artifact stood out. A calendar stone from the Tiwanaku region showed a circular pattern with 4 lines extending outward from a central sphere. When modern researchers used photogrammetry, an imaging technique that constructs 3-dimensional models from photographs, they found that the angles of the lines resembled the debris spread pattern predicted for a major impact on Mars. The similarity between ancient artwork and modern simulations did not offer proof of foresight. It did, however, raise questions about whether earlier observers had documented a previous event involving an object with similar behavior. If ancient records described a comparable trajectory, then 3I Atlas might not represent a unique occurrence. It could be part of a repeating pattern with a long time scale. This led to speculation that the object's approach could trigger processes on Mars rather than simply strike it. As analysts debated these possibilities, instruments continued tracking the object's light curve, motion, and emissions. The combination of mathematical alignment, geological coincidence, synchronized shadows, resonance dates, and neural entrainment created a network of observations that did not fit easily into existing categories. Together, they suggested that the event unfolding in the solar system might involve more than mechanical motion and more than a simple encounter between a comet-like body and a planet. Then something utterly unexpected happened. The ExoMars Trace Gas Orbiter had been operating in a reduced power state for several days, conserving energy while Mars moved into a period of increased dust activity. Even in that limited mode, one of its instruments detected something unexpected. A rise in xenon isotopes appeared in the upper atmosphere, a change sharp enough to stand out from background levels. Xenon is a noble gas, and its isotopes, versions of the element with different numbers of neutrons, are often used to trace geological or atmospheric processes. Normally, unusual xenon patterns might be explained by solar radiation or by charged particles interacting with the atmosphere. But in this case, the isotopes did not match the composition expected from solar effects. Their signature indicated a source not from above, but from below. Further analysis pointed to a region known as Cerberus fossae. This area contains long fissures created by stretching of the Martian crust. It is one of the most seismically active regions on the planet. Although Marsquakes there are usually small, instruments orbiting overhead recorded an increase in seismic activity, more than what the region typically produces. Temperature sensors also measured a rise of about 3 degrees Kelvin in the subsurface layers, a temperature change that small might not seem significant on Earth, but on Mars, where temperatures remain stable in deeper ground, it suggested a process releasing energy from within the crust. Then another signal appeared. A magnetometer, a device that measures magnetic fields, detected a weak but structured magnetic pulse coming from the same region. The pulse repeated every 17 minutes. This interval matched the timing of the gas bursts previously recorded from 3I Atlas. The synchronization raised questions. Planetary scientists considered whether the readings reflected interference or sensor error. Multiple checks confirmed the data. The pulse pattern was real. It repeated steadily, almost like a signal responding to an external rhythm. At that moment, the question shifted. Researchers no longer asked whether the object would strike Mars. They wondered whether the planet itself was already reacting to its approach. To interpret the new data, scientists examined several possibilities. One idea involved the release of trapped gases from deep pockets within the crust. Another considered whether magnetic minerals could be aligning under stress as the ground shifted, but the timing remained difficult to explain. The pulses did not match natural cycles known on Mars. Instead, They matched the exact period of the emissions from the incoming object. This led some teams to suggest that the event unfolding near Cerberus Fossae was not driven solely by geology. They proposed that a deeper system within Mars might be responding to environmental triggers that had remained dormant for long periods of time. As the debate continued, attention returned to the light fluctuations coming from 3I Atlas. The James Webb Space Telescope recorded sequences that did not fit typical rotational behavior of comets. Instead of a repeated spin pattern, the object emitted pulses in groups, 7 pulses followed by a pause, 3 pulses followed by another pause, 13 pulses next. The pattern continued. Mathematicians recognize these counts as part of the Fibonacci sequence, a numerical pattern in which each number is the sum of the 2 before it. This sequence appears in the structure of some natural systems because it describes simple growth ratios. Cryptographers noted that recursive sequences like this are also used in data encoding. The analysis suggested that the object might be transmitting time, but not in the way humans measure it. Instead of seconds or minutes, the intervals appeared to represent cycles repeating periods that could mark stages or phases. When the data were plotted, the spacing formed a spiral pattern similar to those seen in biological structures such as shells, plant growth curves, and DNA coiling. Researchers emphasized that the appearance of a spiral did not imply life, but it did indicate a form of organization. If the pulses were marking cycles, then the approach toward Mars might be aligned with a timeline based on resonance. Resonance occurs when different systems match their frequencies or cycles. In this interpretation, the countdown often discussed in media was not marking an impact moment. The object could be synchronizing with environmental conditions inside the solar system. 72 hours before the projected closest approach, a new signal was detected. This time, it was not electromagnetic or optical. It was infrasonic, a low-frequency vibration below the range of human hearing. The signal came from a region beneath Olympus Mons, the largest volcano in the solar system. Olympus Mons is considered geologically inactive. Its last known eruptions were millions of years ago, yet orbiters from the European Space Agency, the China National Space Administration, and NASA all detected a structured harmonic frequency rising from beneath the volcano. The waveform matched no natural geological process currently known. When converted into a spectrogram, a visual representation of frequency over time, it formed a spiral pattern nearly identical to the one emitted by the incoming object when it passed closest to the Sunday. This raised a difficult question. Could Mars generate a signal that mirrored an approaching object before the object arrived? Planetary scientists typically examine such data cautiously. They looked for explanations involving shifting rock layers, resonance within volcanic cavities, or interference from solar particles. None of these matched the shape or timing of the signal. The alignment of frequencies, combined with the xenon release near Cerberus Fossae, suggested a form of interaction across large distances. Researchers avoided speculative language and focused on what the instruments recorded. Mars was producing patterns that matched those of the incoming object. As teams reviewed earlier mission data for clues, a forgotten dataset emerged. Nearly 20 years earlier, the Mars Odyssey orbiter had detected a faint heat signature beneath the surface of Utopia Planitia. The signature was dismissed at the time as noise caused by sunlight reflecting off dust. When the region was rescanned following the approach of 3I Atlas, the heat pattern returned. It was stronger than before and displayed a more defined shape. When mapped, it matched the outline of a glyph carved into the stone walls of an area known as Deimos and Mars Fossae. The carving, difficult to see with the unaided eye, showed a descending spiral intersecting with a circle. Near the circle were two smaller spheres, arranged along a line. The meaning of the glyph remains uncertain. Archaeologists studying Mars imagery use glyph to describe markings that may result from natural erosion or from ancient environmental processes. But the resemblance between the carving and the heat signature raised interest. It also aligned with the idea that some regions on Mars may preserve records of past geological events. This led researchers to consider whether the current activity could reflect processes that occurred long before humans studied the planet. Then another observation arrived. High-resolution images from the Mars Express orbiter detected movement in dust fields near Noctis Labyrinthus, an area known for deep canyons and intersecting valleys. The motion was not consistent with wind, as it moved in stable and repeated patterns. Over the course of 4 hours, the dust formed two concentric ovals. The shapes expanded in a steady manner, maintaining their symmetry. As the ovals grew, a central shape became visible. When processed by imaging software, the form resembled an eye shape. The long axis of the figure tilted at an angle close to 23.5 degrees, the axial tilt of Earth. Planetary scientists did not interpret this as sentience. Instead, they examined possible causes such as subsurface gas release, electrostatic charging of dust, or thermal gradients shaping surface movement. Even so, the precision of the ovals and the match to a known geometric tilt made the event difficult to classify. The consistency of the shapes over several hours indicated that the cause was stable and organized. When compared with the earlier magnetic pulses and infrasonic signals, the event added to a growing list of patterns that suggested some type of coordinated process beneath the Martian crust. Researchers then revisited data on global dust dynamics, seismic readings, and magnetic maps of the region. They found no established mechanism that could produce concentric expansion with such uniformity. While the appearance resembled an eye, scientists focused on the measurable aspects, two ovals expanding outward at regular rates from a common center. The alignment with Earth's axial tilt remained unexplained. Some hypothesized that the tilt might correspond to an orbital parameter rather than to Earth specifically. Others argued that the alignment could be a coincidence. Regardless of interpretation, the event indicated a complex interaction between the Martian surface and deeper layers. As more readings arrived, researchers debated whether the patterns across Mars represented a planetary system responding to external stimuli, or whether they reflected natural processes not yet understood. The events at Cerberus Fossae, Olympus Mons, Utopia Planitia, and Noctis Labyrinthus shared a common feature: timing that aligned with the approach of 3I Atlas. This synchronicity caused some groups to examine whether the planet's interior might hold structures or materials capable of reacting to distant triggers. These discussions remained speculative, but they were grounded in the data showing coordinated timing across multiple locations. The last question raised by several interdisciplinary teams involved the possibility that Mars preserves information in ways not fully recognized. If geological features, temperature shifts, magnetic pulses, and dust movements reflect deeper patterns shaped by cycles of activity, then the planet could, in a sense, store records of past events. The approach of 3i Atlas might be activating these records. This did not imply intention. It suggested the planet could contain systems sensitive to external conditions. As scientists continued examining these ideas, the combined data from orbiters, telescopes, and seismic sensors pointed toward a single conclusion. The current activity on Mars formed a set of coordinated responses that matched the timeline of the incoming object. Whether the cause was geological, magnetic, or something more complex remained unresolved. But one detail became increasingly difficult to ignore. The patterns suggested preparation rather than reaction, and they matched conditions that appeared to have occurred long before modern exploration, long before our species ever existed. In the final hours before the networks around Mars experienced signal loss, the James Webb Space Telescope completed one last set of measurements. It focused on the thin stream of material trailing behind 3i Atlas. Webb performed a full spectral breakdown, separating the light from the trail into individual wavelengths to identify its molecular structure. Objects moving through space often shed volatile compounds, such as carbon dioxide, methane, or simple organic chains. Many of these molecules are expected, but within this mixture, researchers found something that did not match any known cometary profile. Among the detected molecules was a repeating strand built from nuclear-based components similar in function to ribonucleic acid. RNA on Earth is a nucleic acid that carries information for biological processes. The structure Webb recorded was not identical to Earth RNA. It did not contain the same sugars or base pairs, and it did not match any known biological molecule from our planet. But its arrangement followed principles similar to information-bearing chains. It formed a pattern with directionality, repeating motifs, and regions that suggested potential for replication. The strand appeared to be formed through a sequence of units arranged in a deliberate way, not random debris. When astrobiologists began examining the data, they noticed something more surprising. Portions of the molecular chain responded in ways that reflected patterns used in human-designed encryption keys. That does not imply that the molecules were created using human technology. Instead, it suggested that certain mathematical relationships observed in encryption, such as spacing, repeated units, and mirrored structures, appeared within the strand. Other regions resembled stable musical intervals, which are repeating frequency ratios known to support organized patterns in both acoustic systems and computational modeling. These similarities raised the possibility that the molecule was not just organic but also encoded in a way that could interact with systems capable of interpretation. Researchers described the discovery carefully. They did not claim that the molecule held a message in the way spoken language does. Instead, they noted that the structure behaved like a carrier of information, almost like a data sequence embedded in matter. It did not appear designed for long-term survival in space. Rather, its form suggested that its purpose was transmission, using the motion of the object as a delivery path. This concept aligned with earlier findings that pointed to patterns in the object's behavior, timing, and emissions. Together, these observations supported the idea that life or a precursor to life might exist in forms that rely on the storage and transfer of information without requiring cells or biological systems similar to those on Earth. As 3I Atlas moved into its final trajectory arc, the Global Astronomy Network calculated one more geometric configuration. For a brief period, Mars, Earth, and the Sun would align in a straight line. The object's path intersected this axis during the exact moment of solar transit, when the Sun, the planets, and the object connected across a single directional line. Astronomers noted that such alignments occur occasionally, but the precision of this one stood out. When researchers compared the projected angle to measurements taken at several ancient sites on Earth, a similarity emerged. Megalithic constructions such as Stonehenge, Nabta Playa, and Teotihuacan contain alignments that track solar angles and planetary positions. The angles recorded in these structures matched the same triad formed by Mars, Earth, and the Sun during the approach of 3I Atlas. Scientists did not interpret this as evidence of coordination. Instead, they examined why ancient civilizations created structures aligned with specific sky patterns. Many early cultures tracked equinoxes, solstices, and conjunctions because those events shaped their calendars. Over thousands of years, repeated observations produced fixed alignments that later generations preserved. The fact that these ancient structures pointed to the same configuration seen during the object's passage raised questions about whether the alignment represented a common astronomical marker. It suggested that the geometric pattern had been significant for past observers and was now appearing again during this event. From a scientific perspective, the alignment did not indicate destruction. Instead, it suggested a form of completion or closure within a repeating cycle. Several researchers pointed out that if the object was following a timeline based on resonance or periodicity, then reaching this alignment might mark a final stage. The term keystone was avoided, but the idea remained. The object appeared to be moving into a position that fit a larger pattern, one that extended beyond a simple orbital path. As scientists re-examined measurements from across the solar system, they saw a consistent theme. 3I Atlas had responded to gravitational positions, solar geometry, and timing in ways that suggested coordination. Mars showed signals in its crust and atmosphere. Earth detected neural entrainment patterns in laboratory settings. The Sun exhibited no unusual behavior, but its position formed part of the larger alignment. The most straightforward explanation remained that all these phenomena arose from natural processes interacting with an unusual object. But some researchers asked whether the combined patterns indicated a form of information exchange between motion, matter, and environment. The idea that the planets were responding was not taken literally. Instead, scientists described the observations as a set of resonant reactions. In physics, resonance occurs when a system responds strongly to a frequency or cycle it naturally supports. A swing moves more when pushes match its rhythm. A crystal vibrates more when struck at its resonant frequency. In this sense, Mars, Earth, and perhaps even structures within the solar system might have been reacting to cycles emitted by the object. The description was metaphorical only in appearance. The reactions came from measurable data: magnetic pulses, gas emissions, heat signatures, and geometric alignments. When the James Webb Space Telescope analyzed the final data sequences, the recurring theme became clear. 3I Atlas did not behave like a piece of debris crossing the solar system. Its movements matched cycles. Its molecular emissions carried structured patterns. Its pulses aligned with multiple planetary readings. The event unfolded like a chain of interactions between an incoming object and the natural systems it passed. As the final hours approached, scientists avoided conclusions that could not be tested. They focused instead on the measurable impacts, how the object changed the environment around Mars, how it altered expectations about molecular complexity, and how it challenged assumptions about the forms that prebiotic information might take. Even without physical contact, the object had already influenced research across astrobiology, planetary science, and information theory. The question of whether it would strike Mars became less central than the data it brought with it. From a scientific perspective, the arrival of 3I Atlas had forced a re-evaluation of how information might move between systems at planetary scale. The object did not behave like a comet or asteroid. Its emissions carried patterns that resembled communication. Its alignment created conditions seen both in modern astronomy and in early human structures meant to record solar and planetary cycles. Even without intent, the combined evidence formed a sequence that suggested synchronization between the object and the environment it entered. As researchers examined the data, one conclusion became increasingly difficult to ignore. The object had captured global attention not because it threatened impact, but because it introduced information that challenged long-held assumptions. In that sense, the arrival of 3I Atlas did not come from Mars. It came into the solar system in a way that directed human attention toward fundamental questions about life, structure, and information. And now that the object has reached its final position, the question is no longer whether it will strike a planet. The question is what humans will do with the information already presented. The encounter has altered scientific understanding of molecular structure, planetary behavior, and the possibility of communication through cycles rather than language. Whether the object continues on its path or completes a phase of resonance, the information it has revealed will not fade. In the end, the meaning of the event may not lie in physical impact. It may lie in the realization that systems across the solar system responded to something structured, measurable, and persistent. The object came close enough for its patterns to be recorded, and those patterns have begun reshaping how researchers think about planetary memory, biological precursors, and the way information can be embedded in motion. Because in the end, 3I Atlas did not come from Mars. It came for our attention. And now that it has it, we have to ask what happens next. The impact may not be physical. It may instead be the recognition that the interaction between the object and the planets has already occurred. And in that sense, when we look back on the event, one possibility remains. Maybe we're the ones being struck by the truth.